Alright, we're going to be talking about symmetry today. There's a couple of types of symmetry. The first type we're going to talk about is line or reflexive symmetry. This is one that you've probably heard about. We see linear symmetry all over the place. We might see it in our faces. If we were to draw a line straight down our face, we would notice that both sides of our face look the same as each other. So what we're looking for in linear or reflexive symmetry is where could we draw a line that if we were to fold that shape on that line, we want all the points to match up perfectly with each other. So let's look at a couple of examples. The first one that we're going to look at is this diamond shape. Now, I want to be looking at this shape and I want to try to figure out, is there a way that I can make this line land on top of any of these other lines just by folding it? And what we're really going to do is just draw a line of symmetry. So, if I was to look here, I'm going to notice that this whole thing comes out and back in. And if I look on the other side of it, I'm going to notice it does the same thing. So if I was to fold this shape and bring it all the way over to here, everything should match up. So the line that I'm going to fold it across is going to be right through the middle. So here's my line of symmetry. But that's not the only one that's there. I should also be able to notice that if I was to fold this shape the long way, this point will end up here. So we also have a line of symmetry right through the middle. Now, is it possible that there's other lines of symmetry we could check out, maybe going along the diagonal this way? If I was to fold directly along the middle right there, would everything land right on top of each other? It looks like it probably would. So it looks to me as if I have a line of symmetry through here, and a line of symmetry through here. So if we were to fold along any of those lines, we would notice that everything should match perfectly with each other. Let's look at this other example. Is there anywhere I could put a line to make this thing fold on top of itself? It doesn't look good. I've got this bump out here where if I was to fold it, we would have to have some sort of bump over here. I've got this line down here that if I folded it, we would have to have space missing up here or stuff down here. So this doesn't look like we can do anything. There's nowhere that I can draw a line that we could fold it. How about the Batman symbol? Well, I know that I've got this point down here and I've got the ears up here, so folding it up probably wouldn't work. However, I should notice that on this side and on this side we have curves that match everywhere. Down here matches right over here, up here matches this side. So if I wanted to fold this, I would have to fold it straight through the middle. So this particular example has exactly one line of symmetry. Square. Squares are nice. Squares, I can see that if I was to fold it right through the center, it's going to line up. And I should also notice that if I do diagonally, it'll also match. All of these points will flip over. All these points would flip over. Everything will line up. Alright, rotational symmetry. Little bit different this time. What we're looking for isn't where we can fold it to make the points line up. What we're looking for is if we were to turn this item, could it match on top of itself? So really we should be looking at things that have to do with, length of lines. If we were to turn this shape and make it land, pick it up and spin it, would it be able to land back on top of itself? This is more of a yes-no kind of question. So what we usually look at is, do we have points that can match up? Do we have sides that can match up? I'm noticing that if I spin this particular shape a little bit, it should land right on top of itself. And I can spin it again, and I can spin it again. The key to this is that we want to be able to spin it less than 360 degrees and make it land on top of itself. So this particular shape definitely has rotational symmetry. When we look at this shape, there's no way for us to spin this shape less than 360 degrees and make it look like it originally did, right? If I was to spin this thing 180 degrees, sure, it looks like the same shape, but it's not facing the right direction. We want it to look exactly like it did at the beginning. And it doesn't matter how much I spin this thing, it's never going to look the same as it did when we originally started. So this does not have rotational symmetry. How about Green Lantern's shape? Well, if I spin it a little bit, if I was to bring this point over, I would notice that it's going to have the flat sides on the sides, and the round would be on the top and the bottom. So just a 90-degree rotation is probably not enough. But if I was to rotate this thing 180 degrees, I notice that it looks exactly the same as it did when I started. So I was able to rotate it less than 90 degrees and have it look the same. So yes, this definitely has rotational symmetry. Alright, now we're going to talk about something that's called order. Order has to do with rotational symmetry. What order is how many times can we make this shape land on top of itself, going from 0 to 360 degrees rotations. So we want this thing to land perfectly on top of itself, but how many times can we do it? So, just like rotational symmetry, we're going to have to look. We want to make sure that points like this are going to land back where they should. We want all the sides to land where they should. So if I was to take this shape and spin it one time, I know that I can get this point to line up perfectly. This edge would end up coming down here. Everything matches well. And if I was to spin it again, I would notice that it lands on top of itself again. I could do another one. And if I do one final spin, I end up back where I started. So if I count, I spun it once, twice, 3 times, 4 times. So we would say, for this shape, order equals 4. Looking at this diamond, if I spin this up here, it would be too tall and too skinny. We want it to be wide and long. So I'm going to have to spin this more than 90, but I can see that I can spin this over to here. If I was to spin this all the way around once, it'd land back where it started. And if I spin it around again, I end up at the original picture. So I spun this particular shape 1, 2 times, so its order is 2. How about the X-Men symbol? Well, I do notice I have a circle. So technically circles we could spin infinite number of times. But the trick is this inside part. I want to make sure that this X lands back on top of itself. So what I'm really looking at is, if I spin this to here, I'm going to have the X fall on top of itself. If I spin it again to here, it'll land on top of itself. And I can spin again to here, and again to here. So total, I've spun this shape 4 times before it ended at its original position again. So its order would be 4. And last is magnitude. Magnitude is very similar to, or has a lot to do with order. In fact, in order to find the magnitude, we need to know the order of an object. What magnitude is how many degrees we would spin the object to make it land on itself, just once. Right? So if you think about it, there's 360 degrees in a full rotation. But we only want it to land on top of itself once. So how many degrees would we have to spin it? That has to do with how many order there are. So we're going to take 360 divided by the order, which would be the number of times it would rotate on top of itself, and that's going to give us the number of degrees per turn. So I've got to figure out the order of each shape. I can rotate this particular example 1, 2, 3, 4 times. So for magnitude, I would take 360 divided by 4. That's going to give me 90 degrees. So if I wanted to spin this shape and make it land on top of itself, I would only have to spin 90 degrees. Looking at this next shape, I could spin once, twice, 3, 4, 5, 6, 7, and 8 to get me back to the original. But for magnitude, I'm going to take 360 divided by 8, and that's going to give me 45 degrees. So if I was to spin this one shape 45 degrees, it would land back on top of itself. Our last example is this flower. If I spin it once, twice, 3 times, 4 times, and a 5th time would end me back at the original position. So magnitude equals 360 divided by 5. That's going to give me 72 degrees. So I would have to spin this flower 72 degrees in order to make it land back on top of itself. So that's linear reflection, rotational reflection, order, and magnitude all covered for you. Good luck.